Hello and welcome to this lecture. We have already seen an introduction to inner products and norms, and we saw the usefulness of orthogonality. When you have orthogonality, a lot of things fall into place. A lot of these inner product simplifications are easy, and it helps you in a long way. Okay, so the real power of inner product is that you can find vectors orthogonal to each other, and when vectors are orthogonal to each other, a lot of things using them, linear combinations using them, simplify tremendously. Okay, so otherwise when you have linear combinations you have to do a lot of careful manipulation, but when you have orthonormality along with linear combination, things work so smoothly, and that's at the heart of this notion of an orthonormal basis and orthonormalization. So these ideas are form the crux of a lot of methods which simplify your work when you deal with these big spaces. Okay, so let's look into them. First is notion of orthonormal vectors. What are this? We have this notion of linearly independent vectors which helped us a lot. Now we are going to go towards this orthonormal vectors which are going to help you even further. Okay, they will make your work much simpler. So let's say you have k vectors. When do we say that they are orthonormal? They have to satisfy two conditions. First is they have to be orthogonal to each other, pairwise orthogonal to each other. So if you take Vi, Vj, their inner product should go to 0 for any I not equal to j. Now they should also be normalized, meaning if you picked I equals j here, Vi comma Vi should be 1. Okay, as in the norm of Vi has to be equal to 1 for I in 1 to k. So these k vectors, each of them have to have norm 1, as an inner product of them with itself should be 1. Okay, and the any two inner products Vi, Vj should be 0. Okay, so they should be orthogonal to each other. So they should be orthonormal. Okay, orthogonal to each other and normalized. Okay, so are there such vectors? There are many. In fact, the canonical basis in Fn is a very standard example of an orthonormal thing. So when you take canonical basis, it's 1 0 0 0. So clearly norm is 1. And if you take any two vectors in the canonical basis, it's either 1 0 0 and then 0 1 0. So ones and zeros, whenever there is a 1 here, there will be a 0 on the other vector. There will be no overlapping 1. So when you take an inner product, it will always go off to 0. Okay, so they are orthogonal. So this canonical basis in Fn is an example of a set of orthonormal vectors. Okay, but here is another one. Okay, so these two vectors are orthonormal, right? So the norm is 1, 1 by 2 plus 1 by 2 is 1. So here also 1 by 2 plus 1 by 2 is 1. If you take an inner product here, you get half minus half, you get 0. Okay, and there can be more interesting examples. Here is an example in R3. So you put 1 by root 3, 1 by root 3, 1 by root 3. Notice how I am normalizing here. This root 3. I mean, you can think of it as 1 comma 1 comma 1, but then it's not normalized, right? The norm will become 3. I want norm to become 1, so I'm dividing by root 3. Okay, so when you divide by root 3, then you see 1 by 3 plus 1 by 3 plus 1 by 3 norm is 1. So likewise here, this 1 by root 2, 1 by root 2. But then these two are orthogonal to each other, right? So if you take a dot product, you get 1 by root 6 minus 1 by root 6 plus 0, and that goes to 0. So two vectors being orthonormal looks like it's very easy. Okay. So here is a more complicated example. So I want to spend a little bit of time on this example. So this example involves the cube root of unity. You might remember from your math 1 in complex numbers, we studied this e power I2 pi is nothing but 1, and when you define w as e power I2 pi divided by 3, that becomes a cube root of unity. But we also know how to evaluate e power I2 pi by 3, right? 2 pi by 3 is actually 120 degrees. It's cos 120 degrees plus I times sine 120 degrees. Now cos 120 degrees minus half, sine 120 degrees is root 3 by 2. So this guy is actually minus 1 by 2 plus root 3 by 2 I. Okay, so you can write it in this form. But what's interesting about w is w power 3 equals 1. Okay, so think that through very carefully. W power 3 is 1, and w conjugate is the same as w squared. Okay, so these are all interesting facts about these things. Okay, so let me write it down. W is e power I2 pi by 3. Okay, so if you remember, w conjugate is e power minus I2 pi by 3, which is the same as e power minus I2 pi by 3 into e power I2 pi. So you should remember this. Remember this. This whole thing is on the unit circle. You know. So if you do like this, everything is on the unit circle. This is at like 120 degrees. This is my w. It's e power I2 pi by 3. This picture is very interesting. So when you do conjugate, you get e power minus I2 pi by 3. So it will come off to this side. Okay, this is w bar, which will be e power minus I2 pi by 3. Okay, but it's also the same as if you do I pi, so this is the same as e power I4 pi by 3, isn't it? I can do this e power I 2 pi because this is equal to 1, okay, so you multiply by pi 2 pi. So, this angle is either minus 2 pi by 3 or you can come this way, it will be 4 pi by 3, okay. So, it is the same result, but interestingly 4 pi by 3 is the same as w squared, okay, that is one interesting fact. And the other very interesting fact is w power 3 is actually e power I 2 pi, which I know is 1, okay. So, these are very interesting facts about this cube root of unity, and notice the thing that I have here, it is like this 1 by root 3 1 1 1, okay, and then I have the other vector 1 by root 3 1 w squared, and then the third vector I have is 1 by root 3 1 omega squared omega, okay, w squared w, okay. So, now first property we need to show is that each of these guys, if you want to claim that this is an orthonormal vector, you have to show that each of these guys is normalized, okay, and then the dot products are 0, that is what we have to show, okay. So, if you want, you can do it in so many ways, but you know, this is an interesting thing to remember. You remember this is omega is minus 1 by 2 root 3 by 2 I, omega bar, which is omega squared also, is minus 1 by 2 minus root 3 by 2 I, okay. These things might sound fantastic to you, but this is true. You can do omega squared, you will get this, okay. So, you will see that this will also be true. You can use this and simplify if you like, but let's just do it, right. So, this is V1, let's say V2 is V3, okay. So, if you do V1 into V2, just watch out for the conjugate, okay. The conjugate is the only thing you have to watch out for. So, how will this work? So, you have 1 by root 3 into 1 by root 3, there is no problem with conjugate here. And the second one is 1 by root 3 into conjugate of omega, right. So, 1 by root 3 omega bar will come, okay. And then the last guy will be 1 by root 3 times 1 by root 3 omega squared bar, okay. So, what is omega squared bar, you might wonder. So, that is the same as omega, right, because omega square is omega bar. So, omega square bar is actually omega bar that is just omega, okay. So, you can check all these guys out, it will come out correctly. So, this is going to be interesting. So, if you pull out the 1 by 3 common, you get 1 plus what is omega bar, that is omega squared bar is just omega, and you get 1 plus omega squared, and I have this little bit of an argument to show why 1 plus omega squared is 0, omega is minus half plus root 3 by 2 I, omega square is minus half minus root 3 by 2 I, if we do 1 plus omega squared is 0. Another way to see it is omega power 3 is 1, so omega power 3 minus 1 is 0, and you factor that omega minus 1 times omega square plus omega plus 1 is 0. So, this guy is not 0 clearly, right. So, this guy has to be 0. So, this will be 0, okay. So, in a similar way, very carefully you can compute. So, do not forget the conjugate, okay. So, this is a very common mistake, I have made it several times, okay. I will continue to make it, but you should not make it. So, you will get this V1 comma V2 comma V3. So, you have to conjugate. If you do not conjugate, you will go wrong, okay. So, watch out for that. If you conjugate, use the fact that omega power 3 is 1, use the fact that 1 plus omega square is 0, you will always get back to the thing, okay. So, maybe this one alone I will do. So, V2 V3 you will get a 1 by 3 out, and then 1 into 1 will be 1, omega into omega square bar. So, omega square bar will be omega, so we will get omega squared, and then omega square times omega bar. So, that is omega square into omega square, you will get omega power 4. Now, omega power 4 is the same as omega. So, 1 plus omega squared, it will go off to 0. Okay, so you see how this works. So this V1, V2, V3, they are all orthogonal to each other. And what about the absolute value? This absolute value is 1. What about absolute value of V2? So you do V2 comma V2. Again, don't forget the conjugate, okay. You are going to get a 1 by 3 and then 1 into 1, that is okay. Omega into omega bar plus omega square into omega square bar, okay. So, omega into omega bar is omega into omega squared, which is 1, right, omega power 3. This guy is omega squared into omega, which is again 1. So, you get 1, okay. So, keep remembering the conjugate, you will get to the correct answer, okay. So, this is a very nice basis. So, whenever you have an nth root of unity, cube root of unity, these guys form an orthonormal basis, and these are very, very useful. So, the point is the canonical basis is not the only way to get orthonormal vectors. There are many more interesting such combinations, and this is at the heart of a lot of ideas that we use linear algebra for, okay. So, here is just one nice fact. if you have non-zero vectors, v1 to vk are non-zero and they are orthogonal. Okay, so we'll say non-zero vectors are orthogonal if they are just mutually orthogonal when I use not j. So if you just have these kind of orthogonal vectors, you can make them orthonormal very easily, right? So you just take each v1, divide by its norm. The orthogonality is not going to be sacrificed, right? Because if you just divide by scalars which are real, the scalars are going to come out and you are left only anyway with this. So if the inner product is originally 0, even when you scale it by something, it will continue to be 0. So orthonormality from orthogonal vectors is very easy. Non-zero orthogonal vectors is very direct. So quite often just the orthogonality property is important as long as they are non-zero. If you put 0, then it becomes trivial. Okay. So this is orthonormal set of vectors, and hopefully I have shown you that there are some very interesting looking orthonormal vectors out there, and that's particular importance to us. Okay. Okay, so here are a few other very sort of expected results, but they're nice to write down. It's important to understand them. Okay, so orthogonality plays well with linear independence, and particularly linear combination of orthonormal vectors are very easy to write down. Okay, so let's see why that is powerful. If v1 to vk are orthonormal, then they are linearly independent. Okay, they better be. It's a sort of very easy to show, but you can prove it also, right? Supposing v1 to vk are orthonormal and a1 v1 plus ak vk is 0, then you can show 0 has to mean 0, this, if you take an inner product here, this inner product, this has to be 0, right? Inner product of a1 v1 plus ak vk vi has to be 0 because this is 0. Okay, so it's like 0 comma vi. Instead of 0, I am writing this, so it has to be 0. Now, if you use the property of linearity of this inner product and expand this out, you get v1 vy etc. But then what is v1 vi? 0. Only vi will survive, and this entire expansion will become ai. So basically, in an equation like this, you can sort of take inner product on both sides. Okay, so this is a useful algebraic trick. You have an equality here in vector equality. I am going to take inner product on both sides. What am I taking inner product with? With vi. So if I take inner product on the left hand side with vi, I have this expression. If you take inner product on the right hand side with 0, with v0 comma vi, right? 0 comma vi is just 0 itself. So 0 equals this inner product. So this is a very useful way to think of inner products in a algebraic fashion. So you get here ai is 0. So if any time linear combination is 0, each of the coefficients is 0. So that means they are linearly independent as well. So here is another property. Okay, supposing v1 vk are orthonormal, then the norm square of a linear combination of v1 to vk is simply the combination, the scalar magnitude square. Okay, there will be no cross terms. Okay, so otherwise in general when you write norm square, you have to write it as when you write norm square, you have to write it as inner product of this guy with itself. So there will be a lot of cross terms, right? But all those cross terms will disappear. That's what I have written down here as a repeated use of Pythagorean theorem. But I mean, it's basically, if you write it as inner product of this vector with itself, you will have a lot of corresponding terms, and then there will be a lot of cross terms. All the cross terms will go off to 0 because of orthogonality, and the corresponding terms will give you just the absolute value of a1 squared. So this linear combination plays very well with orthonormality. Okay. So the final definition, which really brings out, makes computations and many other things so easy in these big spaces, is the notion of an orthonormal basis. Okay. So if you have v1 to vn in Fn, we say it's an orthonormal basis. Okay. So supposing you have a basis v1 to vn of Fn, when is it said to be an orthonormal basis? If the vectors are orthonormal. Okay, very obvious definition, but you have a basis of basis vectors, a lot of basis vectors in Fn. If those basis vectors also are orthonormal, then you have an orthonormal set of basis vectors. Now, is it possible? Yes, here is an example, right? Here is canonical basis for Fn. Canonical basis for Fn is an orthonormal basis, isn't it? So it's a nice basis because it's orthonormal. You see that any two vectors in the canonical basis are orthogonal to each other, and they form a basis. Very easy to say. Okay, so yeah, so basically, okay, so here is another fact. Okay, so here I have said a basis, if it's orthonormal, the vectors are orthonormal, it's an orthonormal basis. So it turns out if you have n vectors in Fn, v1 to vn, and they are orthonormal, then they are actually an orthonormal basis. Okay, why is that? That's very easy, right? Orthonormal implies linear independence. When you have n vectors, when do they form a basis in Fn? If they are linearly independent. Now, if they are orthonormal, they are also linearly independent clearly. So this v1 to vn is also an orthonormal basis. So, when you have n different vectors which are all orthogonal to each other, then you automatically have a basis. So, those are the n sort of perpendicular directions you can have in an Fn. Okay. So, here is an example. Okay. So, canonical basis is an example. You may wonder, are there other examples, right? So, here is another example. You can check this. I am not going to check it in detail for you. I already showed you one example. So, this is very easy to check. So, this is R4, right? So, the norm is 1, norm is 1, norm is 1, norm is 1, very easy to check. There is no need for conjugate R4, that way is very easy. So, if you take dot product here and dot product, you see 1, 1, minus 1, minus 1 goes to 0. Dot product here 1 minus 1, 1 minus 1. Dot product here is also 1 minus 1, 1 minus 1. If you take a dot product between these two guys, right, V2 and V3, say 1 minus 1 minus 1, 1. So, it is nicely arranged so that any dot product will go off to 0, 1 minus 1, 1 minus 1. This final dot product also will go to 0, 1, 1, minus 1, minus 1. Okay. So, this is a special basis. Here is another special basis. We already saw that this is a basis. Now, I can say this is an orthonormal basis, right, because this is R4 and there are 4 orthonormal vectors. So, it becomes a basis. Likewise, here this is R3 or not R3, this is C3 now, complex with 3 dimensions. There are 3 dimensions and there are 3 orthonormal vectors. So, automatically it becomes a basis. I do not need to check for linear independence. Okay. I do not have to check that these 3 are linearly independent. I know they are orthogonal to each other. So, the linear independence comes for free. Okay. So, here is an example in C4. Okay. The C4, I have sort of extended this example. Notice how this example extends. Okay. So, watch out for this extension. This is very, very useful. Let me spend a little bit of time on this. Let us say we have omega. Okay, I am saying W, I will say omega now, W or omega, whatever. So, omega is e power I 2 pi by 4. Instead of 3, I am doing 4. I have a primitive 4th root of unity. I mean, the complex 4th root of unity, and this is actually I. If you go to the unit circle and do e power, if you do e power I 2 pi by 4, 2 pi by 4 is pi by 2. So, this is just I. So, this is e power I 2 pi by 4. This is my omega now. Okay. So, this omega is very, very nice. No? So, omega squared is minus 1, omega power 3, right, is actually minus I, right, and that is the same as omega bar, okay, and then this omega power 4 is 1. Okay. So, this is just omega square, omega power 3, omega power 4. So, that is how it goes, right. So, e power I 2 pi by 4, omega square is, so if this theta is pi by 2, right. So, this is the same as e power I pi by 2. This is the same as e power I pi, right, on the other side. This is the same as e power I 3 pi by 2. Okay, this is the same as e power I 2 pi. So, that is how I quickly wrote the pi by 2 multiplication. Okay. So, that is just all that you need about this guy. So, notice how these vectors have been formed. So, the first one is just 1, 1, 1, 1. I have divided by 1 by root 4, which is like the same as this root 3 here. I have divided by root 4. Root 4 could be 2. I am just writing like that for emphasis. The next one is 1 omega square omega power 3. The next one is 1 omega squared, then omega square squared, which is omega power 4, and then omega squared cubed, which is omega power 6. The next one is 1 omega power 3, omega power 6, which is omega power 3 squared, then omega power 3 raised to the power 3 omega power 9. Okay. So, I am going to leave this as an exercise. I have given you enough background here. Check the orthonormality condition for this set of vectors. So, this makes it a basis for C4. Now, this is also a basis for C4, right. This 4 vectors here 1, 1, 1, 1, 1, 1, minus 1, etc. This is also a basis for C4. Okay. These two bases look very different, but they are both orthonormal basis for C4, and these kind of bases are very, very useful in practice. They actually have names. This basis is called the Hadamard basis. These kind of bases with omega powers of unity and this kind of a form is called a Fourier basis. So, this Fourier basis and Hadamard basis are useful quite often in practice, but take this as an exercise. We will see a more general version of it later. You may recall the circulant matrix eigenvectors. They had this form, right? Do you recall that? So, this is also very, very interesting from that context. Okay. So, that is the orthonormal basis. So, we will stop here for this lecture and pick up from here in the next one. Thank you.